This unit is going to cover compound inequalities. So you may have heard the word compound before in English class when you talk about compound sentences. Compound sentences are two sentences joined together by the words and or. So for instance, maybe you want to go out to the movies, but your mom or dad, they've set some stipulations on you, and they said, you can go to the movies if you do the dishes and you clean your room. So how many tasks do you have to complete? You have to complete 2. You have to be able to do the dishes, and you have to do the chores of cleaning your room. However, the word or greatly changes the sentence. You can go to the movies if you do the dishes or you clean your room. So it's a choice. You either do one or you do the other. So how does this relate to math? All right, so if we needed to graph all solutions that are greater than -5 and they are less than 7. So you have to meet both stipulations. Just like you had to clean your room and you had to do the dishes. You had to meet both requirements. So if I am greater than -5, that is all numbers to the right, but I also have to meet the requirement that I am less than 7. So I extend all the way to the left. As you can see, my entire number line ends up getting completely covered. However, I have to meet 2 requirements. So it's really the intersection of the 2 graphs. So the values that fall in between -5 and 7, the intersection is my solution set. So and is a stipulation that both inequalities need to be true for. If I am graphing or statements, so graph x is less than -2 or x is greater than 3. In order to be a solution, I only need to meet the requirements of 1. So if x is less than -2, I am going to the left to represent all numbers less than. If I'm greater than 3, I'm going to the right, graphing all numbers greater than. So the solutions are on either inequalities. This is different with and statements where the solutions have to be true for both inequalities. So an and statement is the intersection. The graph shows shows numbers are solutions of both inequalities. The graph of a compound inequality of or is a union of the graphs, and the graph shows numbers that are solutions of either inequality. So when we're solving for compound inequalities, we are actually solving for 2 inequalities. And statements look a little bit different than what we're used to, but we're actually solving for 2 inequalities at once. So we are solving for -3 is less than -2x plus 1. And at the other end, we are solving for -2x plus 1 is less than or equal to 9. It is not necessary to split the inequality up as I have. You are able to solve by keeping them together as well. So I'll show you that version too. So if we separate them, if I am solving for the left side of the inequality, I'm solving just like we've been doing all year. Normal 2-step inequality. I subtract 1 from both sides. And then I divide out by -2. I am dividing by negative, so I'm going to flip my inequality. So 2 is greater than x. For the right-hand side of the inequality, I subtract my 1 from both sides. So negative 2x is less than or equal to 8. We divide out by negative 2, and we have x is greater than or equal to negative 4, since my inequality had to flip. So graphing that, since smaller numbers go on the left-hand side, I'll place negative 4. So I want to graph all numbers that are greater than negative 4, but at the same time, they are less than 2. And remember, our solution set only lies in between, so it is the intersection of the numbers in between negative 4 and 2. It is not necessary to separate the inequality. You can solve as is. So I just have to remember I'm solving for 2 inequalities at once. So since my goal is to still isolate the variable, get x by itself, I subtract 1 to cancel out my 1's. I just have to make sure I subtract from the front inequality and the back inequality. So I'm left with negative 4 is less than negative 2x, which is less than or equal to 8. Goal to get x by itself again. So we divide out by negative 2, which cancels. I have to make sure that I divide my front inequality and back inequality. 2 is greater than x, which is greater than or equal to negative 4, making sure that our inequalities flipped because we divided by a negative. I'm going to rewrite this. Usually we like to rewrite this so that our smallest value is out in front. So negative 4 is less than or equal to x, which is less than or 2. And I like to look at that as x is bigger than negative 4, but at the same time it's smaller than 2. Therefore, our solutions are in the middle of negative 4 and 2, which is exactly what our graph shows. The solutions are in the middle of negative 4 and 2. Now, some of my students think that when they see an or statement, that means that you can solve either or. You still have to solve for both inequalities. It just means that when it's graphed, it's a union, so they're not going to be intersecting one another. It's not what they have in common. It's either. So all solutions everywhere on the graph counts as a solution. All right, so I'm going to solve the left-hand side to start, so I'm going to add 5 to both sides. So 3y is less than negative 3. Then divide out by 3, so y is less than negative 1 is part of my solution. Then I'm going to solve the right-hand side. So I'm going to add 1 to both sides. 2y is greater than 6. Divide out by 2, and y is greater than 3. So my final answer is y is less than negative 1 or y is greater than 3. Smaller number goes on the left, bigger on the right. So when I graph, y is less than negative 1, y is greater than 3. So we have multiple solutions, and since this is an or statement, any solution that lies on that number line that is smaller than negative 1 or greater than negative 3 is considered a solution.